Okay, so here's the deal. Chapter 7 is all about areas, volumes, arc lengths, surface areas. And yet it's really easy to do all of these things if you just have the right equation. I'm going to start off by kind of going over a big picture, a big idea of how this works. But let's go back to our original integral here. When we want to find the area under a curve, we started off with this whole idea like, well, if we want to estimate this, we would use a whole bunch of little rectangles. And it doesn't matter if those rectangles are the left-hand limit, the right-hand limit, the midpoint, a trapezoid, even if you use Simpson's rule. The whole idea here was it's an estimate. And you can get your estimate better and better if you use more rectangles and make them skinnier and skinnier and skinnier. Infinitely thin, but infinitely many of them. We would add these up by using a summation. We would somehow get this to go and we'd say, oh, well, maybe we want to add up the first 5, or maybe the first 50 or the first 500. But this got really interesting. Oops, probably didn't mean to put the N down there, but you can. If I was going from I all the way up to N, you know what? You can certainly get a whole bunch of them in there if we just let the number of rectangles approach infinity. Now we need to know, how do you get the area of a rectangle? And that's pretty easy. That's just the, what do we say? We say the height times the base. However, when we're talking about this in terms of mathematics, how do we actually get the height and the base? Well, the height and the base, the height's just the function. The actual function tells you how high up it goes, the y value, the height of it. The base is the total width divided by the number of rectangles. Now, when we're doing this with these lovely little summations here, you always start from your leftmost point, and then you would add or subtract or do something where essentially you're saying, gosh, what I'm going to do is each time I want another rectangle, each time I want to find the height of the next one, I'm going to add the width of each rectangle. So you start from whatever your lower limit is plus the width of each rectangle as you go. But then we found out there's a much easier way, to be honest. The only reason I even wrote that up is so you recognize what does this summation look like if it shows up on the AP exam. But right now, there is an easier way. There's a way that eliminates all those summation formulas, all that algebraic work. We realize that if you want to add up an infinite number of them, the way the summation, in fact, this symbol actually stands for an S for summation. The way that we can do that as a shortcut is we just add up a bunch of rectangles where we still have the height times the base. dx is the slight change in the x value. That's the width of each rectangle. F of x is the height at any given point. And that's where chapter 7 begins, because we're going to use that same idea, but just with different shapes. For instance, this is a really weird idea, but what if you actually took a rectangle and rotated it around the x-axis? Guess what shape you'd get? It's called a disc, or a very thin cylinder. And what you could do is, if you added up a bunch of these, you would get a three-dimensional shape where instead of the area under here, now we have the volume of this rotationally symmetric object. You see the area of a disc. Each of those little individual discs is just a circle with a little bit of thickness. A circle times the thickness of it. And so when you're looking at this, it's not that hard to find the volume of that disc. So how do you get the volume of a big object? Well, what you're going to do is you're just going to add up a whole bunch of discs. Pi times the radius squared times the thickness. The integral sums up an infinite number of those little discs. Another example would be, how do you find the arc length of something, the actual length of that curvy thingy? Well, you'd find a whole bunch of distance formulas. So we use the distance formula. I put 3 of them up there. To get a more accurate portrayal, I'll integrate an infinite number of them, very small.